Thanks everyone for coming on your Friday morning. We have a celebrity guest speaker today, Holt Hanley. Holt got a bachelor's degree in earth science from Cal Poly in 2017, and then a associate's in physics from College of Marin in 2019. And then he joined our program in the fall of 2019, my first semester also, and he was in my synoptic meteorology class and was one of the best students. And since he's been here, he's been doing other kind of extracurricular stuff as well. So he developed this YouTube channel that's been very successful. At first, it was kind of meteorology in general, but then he found his niche with wildfire forecasting, and there was just kind of a huge demand for that. And he has over 10,000 subscribers and 1.4 million cumulative views. So very successful channel there that he just kind of did on the side. And Holt's a great researcher, as you'll see today. And I tried to convince him to go on to get a PhD, but his dream was to be a broadcast meteorologist. And unfortunately, he got that job as well, right during his time here. But congratulations, Holt. And so he's at KSBW in the Central Coast, so pretty rare to be able to go kind of straight to where you want to go physically as well. So he didn't have to go to Iowa or South Dakota first before coming back to California. So that's great also. And he's also been a lecturer in Met 10 for us recently. So with that, I'll let Holt take it away and let him tell you what he's been doing with his master's research.
All right, thank you, Patrick, for the intro. I'll just share my screen real quick and go to the presentation. So I think that's probably a good transition to the start of the presentation, where I just want to first off thank Dr. Patrick Brown, Dr. Craig Clements, Dr. Adam Kochansky, Mike Voss, all the people at PG&E who helped throughout this research process. Because while it's me presenting today, it certainly is a team effort. But we'll just get underway. Today, we're going to be looking at the environmental influences on large daily wildfire growth in California. So the first thing that I have to do before we really get into our research is just look at what large daily wildfire growth is. According to this research, we are defining it as greater than 10,000 acres burned over a 24-hour period. So we tried a few different definitions and it didn't really change the results all that much, but we just decided to land on this one because it represents the top 5% of fire days in our data set. And our main goal was to try to figure out kind of what is going on with the most extreme fire days, because living in California over the last few years, we've all kind of grown accustomed to those days. So we wanted to really dive into those. So how I'm going to structure this presentation is really just answering 4 major key questions. And it actually is kind of the story of how the last year or 2 of my research has been kind of going through these different questions. So as I mentioned, lots of large wildfire days in California. Anybody who's been living here the last few years has certainly felt it. 9 out of 10 of the largest wildfires in the history of California have occurred within the last decade. And anybody can think back to September 9th, 2020, where we had basically black skies over us, that San Francisco looked like it was in the middle of an apocalypse. So that's one of the things that sparked my interest into kind of diving into large wildfires. But the main question that I had was, what are the environmental factors that have the largest influence on large daily wildfire growth in California? So you hear lots of different things like high temperature, big wind events, maybe dry fuels, just lots of different things, steep topography. But I wanted to know, it's not just one factor. So what's the actual rank order of what the most important factors are? Then the next question I had was, okay, once we get the rank order of the most important factors, are there any thresholds where large daily wildfire growth actually becomes more likely? So one you've probably heard is kind of high temperatures leads to more wildfire growth. But what is high temperatures? Is 70 degrees bad for wildfire? Is 80 degrees, 90 degrees? Is it just linear as you go up? Or is there some kind of threshold there where we cross a boundary and large wildfire becomes much more likely? Then, once you figure out those different thresholds and all your different variables, is there any trend in the occurrence of days where we cross those thresholds? So just taking, let's say, 80 degrees Fahrenheit, if that's our threshold, do we cross that 100 days per year? And is that more than what we crossed in 1980? Is there an increasing trend, or things getting worse or better? And then the final question kind of ties into how I went about this research. I ended up using machine learning to kind of analyze all this data. And the big question there would just be, was that the right way to go? Or should I have stuck with the traditional approaches, things more like logistic regression, or trying to build like a fire weather indice based on basically like creating some kind of equation or something? So those are the 4 questions. That probably seems like a lot right now, but we will just try to break all of those down and get through this presentation and hopefully answer all of those questions. But before we do that, best place to start is actually just a quick introduction to wildfire. I know there's people listening to this who don't have a big background in wildfire, but the main thing that you need to know is the fire behavior triangle. So it's these 3 different categories that have the largest influence on wildfire, and that's weather, topography, and fuels. I'll just click on some of the variables that we ended up using in our research. I'm not going to dive into those yet or really explain them yet. I'll save that for when I'm actually introducing the machine learning model. But when it comes to understanding why these variables are important, I think the best way to go about it is actually more of a visual representation. So we'll just look at the Caldor fire. If anyone remembers, this was just south of South Lake Tahoe, you can see up there. And as Patrick introduced, said in his introduction, I've been forecasting wildfires for 3 seasons now, and this was the most critical wildfire event that I've ever forecasted for. It was basically taking off over a period of a few days and just going straight towards thousands of structures in South Lake Tahoe. And I like this map because you can actually see the progression of the fire. So the green is where that fire started, then it progressed into that reddish color, and then it finally progressed into that purple and bluish color right there. But then the main thing that you'd wonder just looking at this progression map is, why did it go in the direction it did? And then why do you have some days where it looks like there was a massive amount of growth, and then some days where it barely grew at all? So I think the best way to kind of look at all those different factors and try to answer that question is to check out the fire perimeter here again. You got Lake Tahoe up here. Here's the Caldor fire on August 29th. And throughout the period of 3 days, we'll just look at the weather variables first. It was warm weather. We were in the high 70s. Our relative humidity was around 12%, so very dry air, which then leads to drier fuels. And then we also had gusty winds at about 25 to 35 miles per hour, and they were coming from the southwest, so pushing this fire towards the northeast. And you can actually see that if I turn this on. So we just click on there. You see most of that growth is towards the northeast. Then we go to August 31st, more growth towards the northeast. And then finally, September 1st, more growth towards the northeast. So the big reason for that was we had those strong southwesterly winds mixed with those warm temperatures, mixed with that dry air. But if we zoom in here, we can see that it was more than just the weather variables that were impacting this fire. So there we go. Google Earth is always a little tricky. So if I just zoom in here, you can see that the fire actually appears to stop right where the streets begin. So you notice the fire comes right down here, right where the streets are, that's where the fire stops. And that's not exactly a coincidence. That is because that's where CAL FIRE and the other firefighting agencies were able to get in their resources, their bulldozers, and they basically clear out the fuels right along these streets to protect all the structures and lives in that area. So that's kind of talking about how fuels are important. If you don't have fuels, if they've been cleared out by a bulldozer, your fire is going to stop. If you're up on this hill where it's dense timber that's has a large amount of tree mortality, is extremely dry due to drought conditions, that's where you're going to have a lot of that acreage burned. And then it also matters just what type of fuel it is, and this is in pretty dense timber, so certainly had those fuel conditions there for a big fire. And then finally is our topography aspect. If we look right here, so this is the fire on August 31st. Now, you see it's going uphill, and you might wonder, is it going to go downhill or uphill? But how it kind of works is fire actually likes to go uphill. The reason for that is as the flames tilt over, they're able to preheat the fuels above them. And then you also just get that radiant heat coming off of the fire, which rises, and then it's able to dry out the fuels above the fire. So it's drying them out, all the water is evaporating from them. So then by the time the fire gets there, that tree is just ready to burst into flames. So then if we click on September 1st, you see that most of that growth was in fact in that uphill direction. So that's just a look at the Caldor fire and kind of an example of how weather, fuel, and topography all kind of combine together to lead to the progression that we see within a wildfire. So now kind of gets to the start of the research. And the first thing I should do is probably just show you the area that we're looking at and then talk about the data that we're working with. So this is the area, basically goes from the Oregon border down to around Los Angeles County. And the majority of our research is looking at 2003 to 2020, because that's where the fire data was available. And to see the fire data, small fires, what we're calling small fire days, so less than 10,000 acres burned over a 24-hour period, are those little red dots. The big red dots are greater than 10,000 acres burned over a 24-hour period. So that's our fire data. It comes from 1 kilometer MODIS. It's basically satellite imagery mixed with some of the resources from state and local agencies. And then what's below that is all of our different, what you could call our wildfire factors, all the variables that we're looking at that influence wildfire. So just on this map, I have it organized by fuel type. So you can see that yellow is your grass, green is your brush, the dark green is your timber. But we're working with a lot more variables than just that. Pretty much, if you can name a variable that impacts wildfire, we had it: temperature, winds, humidity, slope, terrain, ruggedness, elevation. If you name a variable, we had to work with it. And the resolution that we're working with is 2 kilometers by 2 kilometers, and it's from a WRF reanalysis. So WRF is a very kind of advanced weather research model that can take observations and physics, combine them together, and basically create a simulation of the environment. Now that might sound a little intense right there, but the best way I like to think of the data we're working with is if you just put yourself on the ground in California and you have your notebook, you have all your weather instruments, and every single hour you're writing down the temperature and then the wind speed, the relative humidity, maybe what fuel you're on, the fuel moisture, the slope, the elevation, every variable. And then you do that every hour of every single day from 2003 to 2020. And then, so you're still standing in California, there's another version of you 2 kilometers to the north, 2 kilometers to the east, to the south, and to the west, doing the exact same thing, all collecting hundreds and thousands of measurements over this time span. And that's basically the data that we're working with for this experiment. So the first thing to do is just, you have all this data and just try to figure out some basic things that are going on. So the first thing would just be to separate it into the 3 major fuel categories: grass, brush, and timber, shown with that yellow bar. light green bar, dark green bar, and just look at the number of wildfires. So number of wildfires on the left here, your years down to 2003 to 2020 on the bottom. And overall, it just looks like most of our wildfires are occurring in grass and timber. Now, whether that's because maybe more people live in grass and timber areas, or maybe there's just not all that much brush in California, can't really say, but that just is what the data is showing. Next thing would be to look at just your years by your fuel type, and then against acres burned. And across the board, it just looks like every single year, most of our acreage burned is in that timber category. And the column that probably stands out the most to you is that 2020, where that was, if anybody remembers 2020, that was where Tropical Storm Fausto was off of Southern California, funneled in a bunch of moisture, created thunderstorms up and down the state, created hundreds of lightning fires, basically overwhelmed resources. And that was when we had those blackened out skies that everybody remembers. So next thing would be to dive in a little deeper and look at just the large daily growth days. So again, that's a very important definition to remember. Large daily growth, greater than 10,000 acres burned over a 24-hour period. So like one day burning over 10,000 acres. First thing would be to see just the number of incidents over time. And it looks like number of large days does go up around 2007, 2008, seems to go down around 2010 and 11. And then from 2014 to 2020, basically looks like a steady increase, except for 2019. And then when it comes to the number of incidents, this one was actually pretty interesting to me because I always thought October was the peak of wildfire season because that's where you haven't had rain for a very long time, dry fuels, and then you start getting those offshore wind events. But according to our research, it looks like August is actually the peak of where you see those large daily growth incidents. So those are some of the kind of the basic questions. But then we want to look at exactly what are the environmental factors that lead to those large days. So easiest way to go about that is just basic logistic regression, where you plot variable on the x-axis, daily acres burned on the y-axis, and see what the correlation is. And my thinking was, whichever one has the highest correlation, that's the one that's most important to wildfire. So we've got temperature against acres burned, wind speed, relative humidity. And it does look like you maybe get more of your large fire days as max air temperatures goes up, maybe more of your large fire days as relative humidity goes down. But when you actually look at the correlation in your red line there, it basically looks flat, which I think was one of the biggest surprises throughout this research. And my explanation for that is all of the factors kind of are so interconnected and rely on each other that it's really not one factor that is the most important, but it's actually the kind of interplay between all the different factors and how they all combine to create a big fire day. So then I was thinking, okay, maybe the right way to go is something like the fire weather indices, because those are something that do combine those factors basically into an equation to tell you about fire danger. So I calculated the 3 of the top indices out there. We've got hot, dry, windy, Sharples, Fosberg, and then I just put those against acres burned. And the correlation did look better. You see that red line is slightly more sloped, but overall, not exactly what you would want to see. And it just, yeah, it's just not good enough of a correlation for what we're looking for here. So then the final one that I was thinking is, all right, drought has to have a huge correlation with wildfire. The drier the fuels are, worse wildfire is going to be. So this is just an example of your drought map right here. And the thing I want you to notice is the colors that we're looking at. So orange is your severe drought. That bright red is your extreme drought. Burgundy is that exceptional drought. And then just for example, looks like burgundy, exceptional drought right there for California right now. It's about 16% of the state is in that color. So what I did is basically took this map and did a time lapse of it over the years we're looking at, which is 2003 to 2020. So first thing is to look at this left y-axis. That's percent of state in these different drought categories on a monthly average. So I'll just take a slice of this data to explain what's going on in this map, because at first glance it is a little confusing. So we'll just go right before 2008. It looks like 100% of the state is in that yellow color, which is abnormally dry. Then if we go to the orange, which is severe drought, go over, it looks like about 65%. That bright red color, about 35% of the state in extreme drought at that point, and doesn't look like any exceptional drought there. And then it's time lapsed across time, so you can see where you have more drought, less drought, more drought, and then less drought again. And then on this right y-axis, we have monthly acres burned, and that's shown with the black shading overlaying the drought conditions. So just looking at this, we'll just start around 2006. Looks like there was very little drought conditions, and our acreage burned wasn't all that much. Then around 2008, looks like those drought conditions really jump up, and we do get that spike in acreage burned. Then around 2011, looks like our drought improves, but then acreage burn goes down. And then the big one, around 2020, drought conditions go way up and we get that massive spike in acres burned. So just looking at this, it would seem that there is a correlation between drought and acres burned. But if you actually just take the drought severity index and put it against acres burned, almost no correlation whatsoever. So at this point in my research, I didn't exactly know where to go from here, because everything that I tried was basically just showing no correlation, even though intuitively you know these things are correlated. But once again, I think the problem is it's not one individual thing that leads to those big wildfire days. It's actually the connection between all of those variables. So the way we solved that problem is by introducing machine learning. And there's kind of two main reasons that we did this. The first one is it solves that problem where we're not just trying to draw a straight line through the data or look at one variable at a time. Machine learning can basically figure out a complex relationship and is able to understand how different variables are interacting with each other. And then the second reason that we went with machine learning is it also just takes the experimenter out of it. Like before, it kind of felt like, all right, I know drought's correlated, so let's see if it is. And how can I look at this to show that drought is correlated, or how temperature is correlated? Or what if I were to multiply wind and humidity together and then make an index about that? But I was kind of imposing what I already was expecting to see on my research. Whereas with machine learning, you just feed it the data and then the model does the rest. It figures out what's going on just based on the data itself. So it kind of takes the experimenter out of it, except for the selection of the variables that you're going to use. And then when it comes to the variables that I decided to use, it's basically over hundreds of tests, trying all kinds of different variables. And then I picked the best 9 using 3 from each side of the fire behavior triangle. So for weather, we've got max air temperature, min relative humidity, and daily average wind speed. The reason I went with max air temperature and min relative humidity is that usually happens at the peak of the afternoon, which is when you're seeing most of your large growth. And then daily wind speed, just because that performed better than your average wind speed. And then those 3 variables performed better than any other weather variables. And then for topography, we've got terrain ruggedness, which is, you can actually just think of that as flat versus hilly terrain. So it kind of takes into account whether you're going to have a bunch of canyons or hills or mountains, that kind of stuff. And then slope is how steep that terrain is going to be, kind of ties back to what we're looking at with the Caldor fire, and then elevation as well. And then for fuels, we've got 100-hour dead fuel moisture. 100-hour, you can just think of fuels about the size of your wrist. And then fuel moisture just means how much moisture is in that fuel. How I always think about this is if you've ever started a campfire with a dry log and a wet log, intuitively you just know that the dry log is going to be a lot easier to start that fire, and then it's going to burn a lot hotter and faster. So dry fuels typically lead to more wildfire. Then soil moisture, that one's easy, just how much moisture is in the soil. That's most likely going to affect how dry your fuels are. And then live fuel moisture, chamise. The reason I chose chamise there is that's kind of the main vegetation type that wildfire researchers go to in California, because it's a plant that's kind of available to researchers throughout the state. So for example, if Northern California researchers looked at fuel moisture on coastal redwoods, people in Southern California would have nothing to compare it to. So chamise is just a good variable to look at so that it's comparable across the entire state. So basically what happens is we take all of these variables and put it into the model, and then it tries to predict whether it's going to be a small fire day or a large fire day. So for example, let's say it's 50 degrees, maybe 50% relative humidity, your slope is very flat, and it just rains, so your fuels have a bunch of moisture. The model probably going to predict small daily wildfire growth. And if it doesn't predict that, then it's going to learn that it was wrong. Now let's take another example. Let's say our temperature is 80 degrees, it's relative humidity in the single digits, steep terrain, fuels are exceptionally dry. The model probably going to predict large daily wildfire growth. And if it doesn't, it's going to learn how or why it was wrong. So this whole model was trained and tested on 16,000 individual fire days. So how I like to think of that is almost like you're playing darts, where, and this is basically just an analogy from machine learning. You're playing darts and you throw a little bit to the right. So then you think, all right, maybe I should tilt my shoulders. You throw a little bit to the left. And then over time, if you practice throwing 16,000 darts, you're going to get closer and closer to that bullseye. That's basically exactly what the machine learning model is doing. It's looking at data, making a prediction, seeing if it was right or wrong, and then adjusting and learning over time until you basically build a model that can predict large daily wildfire growth. Now, once that model is built, the first question that you're going to ask is the model actually good? So that's where what's called an ROC curve comes in. And at first glance, this isn't exactly intuitive. So we're just going to look at the different axes right here. So on this left side, that's our true positive rate. What we're trying to predict is large daily wildfire growth. True positive represents when there was a large fire and our model predicted a large fire. Then on the bottom here, that's where our model predicted a large fire, but it was actually a small fire. So the model was wrong. So if your model is perfect, it's going to get every large fire correct and never guess a large fire when it was actually small. And your blue line right there is going to go all the way up to this 1.0 on the top left. Now let's say it does not get one right. That blue line is not really even going to be on this graph because it's going to be down in this bottom right here. And then kind of your measure of how good the model is how much area under the curve you have. You're going to have a lot more if it's close to that perfect 1.0, and you're going to have a lot less if it's closer to where you've just been getting a bunch wrong. But the exact performance indicators is 0.5 to 0.7 is considered poor, 0.7 to 0.8 is acceptable, 0.8 to 0.9 is excellent, and then 0.9 to 1.0 is outstanding. And our model ended up getting a 0.831. So that puts it in the excellent category. So just right there, you could say, all right, this model is excellent at predicting large daily growth given these 9 variables. So just right from there, you could use it for forecasting. But since this is research, we really want to actually dive into the model to see kind of what's under the hood. And what's interesting about machine learning is it's always been, a downside of it has always been the fact that the experimenter is kind of pulled out from the research. So sometimes it's considered a black box approach where the model just looks at all the data, it figures out what's going on, and then the researcher is kind of left in the dark. But that is starting to change thanks to what are called Shapley values. So this actually this kind of method actually originated in game theory, but it's a way to basically pull back the curtain and figure out what's going on within your machine learning model. And I'm not going to get too into the data science part of this because we're mostly interested in the wildfire and meteorology aspects. So the only thing I'm going to focus on this one is just that red color that you see next to your variables. So 100-hour dead fuel moisture, as that one goes down, you see more of that red color, and that's where it's going to be correlated with your large daily wildfire growth. For max air temperature, as you go up, you see that red color. That means it's more correlated with large daily growth. So this graph right here is basically just a test to see if everything is correlated the way that you would expect it to be. And it all checks out, goes along with kind of the universal understanding of wildfire factors. So right there, looks like we're off to a good start. The model was picking out relationships that people have seen in nature. And then the next question would be the big question that we started this research with, which is, all right, what's the most important? And this is where a waterfall plot comes in. The only thing I really want you to look at right now is the blue bars and then the numbers on the top. And this tells you how important that individual factor was to the prediction, and it's ranked in descending order. So our most important variable when it comes to large daily wildfire growth is 100-hour dead fuel moisture. And it looks like it makes up about like 18% of the model's predictive ability. Coming in at number 2 is max air temperature. Looks like that's maybe 17%. And then soil moisture at number 3, around 5%. Then at the bottom, the ones that aren't impacting our model all that much, looks like slope, elevation, and you notice wind speed. So anybody who knows anything about wildfire probably just raise their eyebrows, because we all know that wind speed is very important to wildfire. We saw that on the Caldor fire as it took off towards the northeast. So the question is, why does the model say it's the least important? Few possibilities on that. One is, since our fire data was on a daily time scale, we had to take our hourly wind speeds and just get a daily average, and we lose a lot of that resolution there. So I think, in my own opinion, if we had hourly fire data, I think we would, and be able to combine that with hourly wind speeds, I think wind speed would jump up on this list. And then the other factor that's going on here is our model data doesn't account for how wildfires create their own winds. That's one of the big things that we study at San Jose State. We know how important that is, and that's something that isn't included in this research. But I think both of those, just maybe some nice topics for future research down the line. But there is actually one possibility or one explanation that does kind of show why maybe the model wasn't identifying wind speed as an important factor. And it comes to these histogram plots. So the main 4 variables that we're going to be looking at right here, and then we're actually going to be looking at throughout the rest of this presentation, are 100-hour dead fuel moisture. Reason for that, it's the most important variable, so I want to dive into that one. And then our 3 fire weather variables. So we have max air temperature, min relative humidity, wind speed. Main reasons I chose to look very closely at the fire weather variables is I'm very interested in wildfire forecasting, and these are the variables that change the most rapidly. So if you're waking up in the morning and if you want to know there's going to be a large wildfire day, your topography didn't change at all from yesterday. Your fuels changed very little. You're really going to want to emphasize those fire weather variables to decide exactly how bad the day is going to be and how different it's going to be from previous days. And getting my master's in meteorology, interested in weather. So of course, we're just going to look at these variables. All right, so what's going on in these figures right here is this is putting the model aside for a second and just looking at the data itself. So imagine you have your big pile of all your data and you're going to separate it into two different kind of piles. One pile is your small fire days. One pile is your large fire days. So your large fire days represented with the orange color, your small fire days represented with the blue color. And then you're going to look at them depending on the different variables. So we see in the top left here that as you go down in fuel moisture, you see a lot more of those large fire days. Looks like most of your large fire days are between about 5 to 10% dead fuel moisture, whereas your small fire days a bit more spread out. But overall, pretty big separation. For max air temperature, you see that big separation as well, with most of your large fire days appearing as you get warmer. You can actually see the mean if you look at the lines there. So your mean on large fire days, again, this is the data itself, not the model, is 87 degrees Fahrenheit, whereas your small, that's around 71 degrees. Then for min relative humidity, looks like there's kind of a moderate amount of separation, but certainly not as much as what we're seeing for dead fuel moisture and max air temperature. And then wind speed looks like there's barely any separation at all. So my kind of hypothesis is that the ranking of this separation here is something that the model is able to use and pick up on to create its feature importance. So just coming right back here. So you notice the two figures where we had the largest amount of separation, those are our 1 and number 2 features in order of feature importance. Then at number 6 was our relative humidity. That showed our moderate separation. And then wind speed, which barely had any separation, that came in at last. So basically what I'm saying is the model is able to pick up on these differences, and that's one of the things that it uses to make its prediction. And then one other thing that I will mention on this graph that I didn't mention before is what this blue line is. That basically shows the cumulative ratio of your model. So if you were to just take your top 3 variables there, 100-hour dead fuel moisture, max air temperature, and soil moisture, those 3 variables combined make up about 50% of the model. And then you notice as you go down the curve, each variable adds a little bit less than the one before. So that's basically our model and kind of some of the key things that we're looking at right there. But now we want to dive in a little deeper, answer our next question, which is, we know what environmental factors are the most important now. Looks like 100-hour dead fuel moisture, max air temperature, very important, but are there specific thresholds where those variables become more dangerous? You could put it that way. Is there a threshold where it changes from small growth to large growth in that prediction? And that's where we're going to use Shapley values again. And once again, looking at those same 4 variables, our most important one, along with the 3 fire weather variables. So we'll just dive into 100-hour dead fuel moisture first. Bottom, you can see that's the percentage of your fuel moisture. So 5%, that's where it's very dry fuels. 30%, that's where it's very moist fuels. Next thing I want you to look at is that 0 line going across the middle right there. Below that 0 line, that is where this individual variable is pulling the model in the direction towards small daily growth. Then above that 0, that's where this individual variable is going to pull the model towards large daily growth. So what's cool about this is you can see the point at which it crosses the 0 line. And this is something that's actually, to my knowledge, I'm the first person to do this. I used a technique called locally weighted scatter plot smoothing to kind of get what you could think of as kind of the trend line between all of these individual fire days, which are represented with those blue dots. And with that, we can see exactly where it crosses 0. Or in other words, we can see the point where this variable is going to stop pulling the model towards small fire days and start pulling the model towards that large daily wildfire growth prediction. So 400-hour dead fuel moisture, it looks like it transitions at a threshold at 10%. And what's interesting about this is this actually goes along with something that PG&E saw as well, where they saw that at 10%, 100-hour dead fuel moisture, below that was where they saw most of their large fire days. Above that, didn't see very many large fire days. Now, the next one to look at is max air temperature. Once again, below zero, think small fire. Above zero, think large fire, according to this variable. And it looks like it transitions at a max air temperature of 75 degrees Fahrenheit. Then coming to min relative humidity, first thing I notice is that the curve isn't as steep, but it does transition at a threshold of about 17%. And then finally, for wind speed, looks like it's around 7 miles per hour, but again, we can take the wind speed with kind of a grain of salt because that was the factor that impacted our model in the smallest amount. Now, one other thing that I do just want to point out here that I can imagine somebody had this question pop up, so I'll just answer it ahead of time. You might be wondering why this max air temperature curve comes down. Like you would just think as temperature goes up, wildfire gets worse, but it looks like it almost peaks around 90 degrees. My hypothesis for that is as you get into 100 degrees, 110 degrees, you might be getting into some of your desert regions. So even though your temperature is going up, there's just not enough fuel there to lead to those big fire days. So I think the model is kind of accounting for that. But overall, as you get warmer, wildfire danger goes up and it seems to transition from small to large fire at a threshold of 75. So we have our thresholds. Now we probably want to check and make sure some of these thresholds are valid. So the first one, 100-hour dead fuel moisture, I already said that kind of went along with what PG&E has seen in their research. Some of the top wildfire researchers probably in the world working at PG&E. And then overall, I couldn't find very many studies that have looked at wildfire thresholds before, but I did find this one from 2008, and I highlighted this line right here, where they're looking at live fuel moisture chemise, and that was one of the factors that I looked at, and I identified a threshold of 70%. And then in this paper, this highlighted line, although most large fires occurred after the less conservative 71% threshold. And then what I think was the most amazing part of all my research, or the most exciting kind of validation that I got in my research, especially during COVID, where you're kind of working in a bubble, you don't actually know if what you're doing is right. Although certainly getting lots of help from lots of people, but this line right here, Piersco and Green, 1967, suggested that fire behavior transitions at a live fuel moisture threshold of 70%. So right there, that shows that using all these fancy techniques like machine learning, Shapley values, locally weighted scatter plot smoothing, we identified the same threshold as a study from 1967 using completely different methods. So your first thought might be, well, we used all this fancy stuff and didn't improve at all. We just found the same thing. But if something is real, it's not going to change over time. So that's, to me, just a perfect validation of what we're doing. And it also shows that the other numbers that we've figured out are most likely valid as well. So the thing that differentiates our study is we're able to find all kinds of threshold values for all kinds of variables, and we're able to do it at a few clicks of a button versus this study, which I'm sure had to go out in the field, collect fuel moisture data, all that kind of stuff. So overall, just good to see that our threshold values are validated. All right, so next question would be, how many days per year are these thresholds being crossed, and how has this number changed over time? So we've got our same four variables here, and on the top one, we're just going to look at 100-hour dead fuel moisture and our threshold of less than 10%. With the colors, just think blue color, good for wildfire, red color, bad for wildfire. And this kind of color bar might be a little confusing. It's days per year per year. Best way to think about this is we'll just pick a spot. We'll take the Santa Cruz Mountains, which looks to be in that bright red color, which is maybe 2. What this is saying is that if in 1980 you had 100 days where you crossed this fuel moisture threshold, in 1981 you had 102. In 1982 you had 104. So every single day you're adding 2 days per year where you're crossing that threshold value. So basically lengthening your wildfire season, or the days where large daily growth is more likely. So overall, whole state, basically bright red, not what you want to see. And I do want to point out again that the trends that we're looking at now is a new data set, and it goes from 1980 to 2020. So we're taking the thresholds from our machine learning and our research and then applying them to look at trends over time. So our next one was max air temperature. This one, not as extreme, but it does look like the entire state is in that slightly red category. So it does appear that things are more days per year are crossing that danger zone for max air temperature. Then look at min relative humidity. Not a big surprise because you would expect this to be somewhat correlated to your fuel moistures. That's another one where most of the state looks to be in that bright red category, meaning there's more days per year where we're crossing that threshold where relative humidity starts leading to that prediction of large daily wildfire. And then finally, we've got wind speed. This one's a bit more of a mixed bag, just light red, light blue, but overall maybe looks like the majority of the state is in that light red. And some of our key fire danger areas, like the North Bay, do look like they might be getting slightly windier. So next thing that we're going to look at is just a representation of those trends across time. So again, same 1980 to 2020, same 4 variables, but now we're going to basically take that map of California and average it into a yearly value. So we'll look at 100-hour dead fuel moisture first. And in 1980, looks like we were crossing that dead fuel moisture threshold 135 days per year on average throughout our domain. Then if we go to 2020, it looks like we were crossing that 185 days per year. So what you can do is look at that red line, which is your trend. And in 1980, it looks like we were around 125. In 2020, looks like we're around 175. So in other words, we have 50 more days per year where we're crossing that threshold, where our most important variable when it comes to wildfire danger is in that danger zone. So almost 2 more months. Now, when we come to max air temperature, increasing in the direction you wouldn't want it to, but it doesn't look as extreme. Looks like it goes from about 125 to about 135 days per year where we're crossing that threshold. So about 10 more days over that 40-year time span. Then for min relative humidity, our 17% threshold. This one, once again, looks pretty extreme. Goes from about 80 days in 1980 up to about 120 days in 2020. So 40 more days per year where we're crossing that min relative humidity threshold than what we had back in 1980. And then finally winds, that one almost flat, just a slight increase of about 5 days per year. So we've identified what the most important variables are. We've identified the thresholds. We've identified some trends. Now let's see if machine learning was in fact the right way to go, comparing it to traditional approaches. And how I did that was through basically 5 different experiments. So the first one is just comparing our model, which is on the left here. Remember that 0.831 excellent predictive power against a logistic regression model, which think of that more of just straight line. Machine learning, think of it as complex function. And right off the bat, looks like logistic regression has an acceptable value using all the same variables, but it's not as good as our machine learning. So next question might be, well, maybe that's just because it's using the individual values, and maybe it is actually still better to package them into a fire weather index and just make a model out of that. So once again, I built the Sharples, Fosberg, and hot, dry, windy indices, and then tried to use that to predict small or large fire. And this actually just had terrible predictive power. Average, I believe, was about a 0.581 across the board. So in this aspect, putting all our individual factors in our normal baseline random forest model significantly outperformed the fire weather indices. Now, it's also kind of understandable because a lot of these are mostly just looking at our weather variables, so you lose some of that fuel and topography that's going on. So the next thing I thought is, what if I use these fire weather indices, but then I keep the topography variables in there, so our terrain ruggedness, slope, and elevation, and then I put in another index to represent the fuels. So it's basically a battle between my model, which is individual variables, versus kind of an index model. So on this far left, we have the Sharples fuel moisture index representing our fuel variables. So you take out your 3 fuel variables, put in your fuel index, and then you put in Sharples fire weather index instead of your weather variables. And it does better than when it's just the index by itself, but it's still not as good as our model, which was the 0.831 versus that one, which is a 0.788. Then I tried the same thing with hot, dry, windy, representing the weather variables, and then what's called energy release component, representing the fuel variables. You could just think of that as a fuel index. That one did pretty well, 0.809, but still not as good as the random forest model that we used. And then finally, I tried it with Fosberg and energy release component, and once again, 0.792, not bad, but not as good. So what this tells me is that putting in the individual variables and just letting the model do the work and figure out what's going on is a better technique than basically the traditional approaches. So 2 more experiments left. These were just kind of fun ones, just to kind of dive into this stuff. And I basically took our giant pile that we built our model with, and I separated it into 3 piles based on the 3 major fuel types. So we have grass, brush, and timber. So right off the bat, I was actually expecting our model performance to go down. Like going back to the dart example, if you practice 16,000 times, you're going to get better than if you practice 5,000 times. So with machine learning, usually more data, the better. So I thought when we separated into 3 piles, things are going to get worse, but actually the exact opposite happened. You can see our grass model here, once again, just using all the same variables that we used, goes up to a 0.857. Brush model goes up to a 0.85, and then timber still excellent results at 0.824. So what that tells me is that fire behavior is different enough within the different fuel types that is actually more important to your machine learning model than just a large amount of data. And then the one other kind of interesting thing, and as just an example of some of the information you can pull out of this, is let's just look at the topography variables here. For grass, topography comes in at number 2 with terrain ruggedness and number 4 with elevation. With brush, our topography was the number 1 variable with slope, number 2 variable with terrain ruggedness. And then for timber, topography was our worst performing variables. All 3 of them were at the bottom 3. So that's just saying topography appears to be fairly important for grass and brush, but not so important with timber. Just one interesting little nugget of information you can pull out, but you could look at these all day and just figure out all kinds of things. Now, final experiment, and this is actually the one that I was most interested in, is we talked about our fire behavior triangle, fuel, weather, topography. I wanted to know which side of the fire behavior triangle is the most important for wildfire forecasting. And being a meteorologist, I'm not going to lie, I was rooting for the weather side. But a reminder, this is machine learning, so I'm just feeding it data, and my bias isn't going into these results. But I basically built the exact same model as before, and then just eliminated sides of the fire behavior triangle. So on the far left here, I just took out the weather variables. In the middle, I took out the fuel variables. On the right, I took out the topography variables. And however much the model's performance goes down, tells you how important that side was. So we see weather, no weather goes to a 0.79, no fuel, 0.81, no topography, 0.793. Or in other words, if you take out weather, your model becomes worse than any other ones because weather is the most important. Now that's kind of using kind of some negatives. So we'll just do a more kind of easy way to understand it. What if I'd build the model with just 3 variables, only weather, only fuel, or only topography, and see what the predictive power of that is? Basically testing the same thing as before. When it's only weather, surprisingly does pretty well at a 0.791. If it's only fuel, it's acceptable at about 0.736, and only topography pretty bad at a 0.676. So in other words, according to this research, weather provides the largest amount of predictive power for large daily growth. So I'm sure all the meteorologists out there love to hear that. All right, so in conclusion, we're going to go back to our 4 questions. What environmental factors have the largest influence on large daily wildfire growth in California? The big 3 for our baseline model was 100-hour dead fuel moisture, max air temperature, and soil moisture. Although we did see that variable importance changes depending on the fuel type that you look at, which I would say makes intuitive sense. So once we had our rank order of our variables, we looked at what are the thresholds where we transition from predicting small daily growth to large daily growth. And it looks like it's 10% for dead fuel moisture, 75 degrees for max air temperature, 17% for min relative humidity, and 7 miles per hour for wind speed. Then once we have these thresholds, how often are they occurring? And is there a trend across time in how often we're crossing those thresholds? So we looked at that. The alarming ones were for 100-hour dead fuel moisture and min relative humidity, where we're seeing 50 days or 40 more days per year where we're crossing those thresholds. And then max air temperature and wind speed increased by 10 days and 5 days. So moving in the wrong direction, or the direction we wouldn't want it to be moving, but overall not as bad as our moisture values. Then finally, we compared our machine learning model against more traditional approaches, against a logistic regression model, outperformed it, and then against the indices, it significantly outperformed it. So overall, I think the takeaway there is that machine learning has some very big advantages. And I think with further research, I think it's going to be a massive part of how we forecast large wildfire days in the future. So just a final conclusion, the takeaway line, if you didn't listen to anything else in this entire presentation, the most important variable when it comes to predicting large daily growth is 100-hour dead fuel moisture. It transitions at a threshold of 10%, where below that, more large fires are likely. And we're seeing 50 more days per year where we're crossing that threshold. So some alarming trends out there, but that's where San Jose State and our fire weather research lab comes in, and all the work that we do here, especially with work as well. And hopefully we can continue to be part of the solution to wildfire in California and continue to uncover relationships that help us forecast these events in the future. Thank you.